Good evening, everyone, and welcome to today's session of Essence Training Series. We'll start with yesterday's session where Dr. Ghosh left, and then we'll continue to today's session. And today's session will cover the horizontal and vertical irregularities. And with this, I will transfer the mic to Dr. Ghosh.
Thank you, Bodhi, and good evening. We are in the middle of discussing the equivalent lateral force procedure of seismic design of BNBC 2020. Time ran out on us yesterday, so I will pick it up where we left off, except that we discovered an error yesterday in these numbers. In one of the in the example that I was showing you, in calculating S sub A, the spectral acceleration in that period range between T sub D, which is 2 seconds, and 4 seconds, which is the end of the spectrum, the soil factor S, which is 1.35 in our case, was taken mistakenly as 1.25. That resulted in 5 here, but the actual number is 5.4. So this was 3125, that becomes 3375, and we get the final result S sub A at 4 seconds as 009 or 0.9%. It was 0.83% when I had the wrong number of 1.25 for S. And now, with the correction made, there is no difference between the BNBC number and the ASC 705 number. Yesterday, there was a line which I deleted that said this 0.9% is slightly different from the 0.83% we had derived by BNBC 2020. Okay? So please note that correction BNBC and ASC 7 gives you identical numbers as it should. Let me get to the place where we left off here. So this is the slide that I did not start on yesterday. Let me maybe do it this way. I may have to go a long way back. It may not be worth it. Okay, the base shear V is S sub A, the spectral acceleration, multiplied by the seismic weight W. The spectral acceleration S sub A, unless you are in the flat top portion of the spectrum, is inversely proportional to period or period squared. So we had to discuss the period itself. And then in the equation for S sub A, we had R and I. So we need to discuss the R and the I coefficient. The seismic weight we have discussed already. So let us start with R. R is given for each structure. Well, let me put it this way. There are in table 12.2-1 of AC 705 a number of seismic force resisting structural systems are listed. The total number of systems is somewhere in the 70s. For each system, we are given 3 parameters: R, C sub D, and omega sub 0. all three actually need explanation because all three play important roles in seismic design, although omega sub zero probably a little bit less so than R and C sub D. Okay. So let us look at this picture where I have drawn the force displacement relationship of a particular structure subject now to the design earthquake of BNBC 2020 or AC 705. So one structure subject to the design earthquake of the code. The forces induced in the structure as it goes through the design earthquake are on the y-axis, and we have specifically plotted the base shear V, and on the excuse me, on the x-axis are the displacements suffered by the structure, the lateral displacements as it goes through the design earthquake of the code. Okay. Now, this line shows hypothetical elastic response. If our structure were to respond elastically to the design earthquake of the code, it would have developed a force equal to V sub E and would have suffered a displacement, total displacement equal to lowercase delta sub E. Okay. You know by now that we do not design our structures to respond elastically to the design earthquake. So we design for a much lower force level than V sub E, and that design force level, the design base shear is V. Okay. Now the ratio between V sub E and V is the response modification factor R. Now that is a little bit simplistic. There are complications in it. Complication may not be the right word. There are other aspects to it. When we design a special moment frame of concrete or steel for an R of 8, we are not designing for 1/8 of the force level that would have been needed for elastic response to the design earthquake. We are designing, our force level is more like a quarter of the force level that would have been needed for elastic response to the design earthquake. Just keep that in mind. I don't want to go any more into that. It gets a little bit complicated that way. So R is the response modification factor. Simplest way of looking at it is the ratio between the hypothetical elastic design base shear and the design and the base shear we are actually using in design. Okay. Now, this design base shear V is distributed along the height of the structure in the manner prescribed by the code. And we will look at that distribution in a little bit. When we elastically analyze our structure under those distributed forces, we get lateral displacements at the various floor levels. The lateral displacement at floor level X is denoted by lowercase delta sub X for floor level X, E for elastically computed. So delta sub XE is the elastically computed lateral deflection at floor level X under the code prescribed seismic forces. The design base shear distributed along the height of the structure in the manner prescribed by the code. We know that if the design earthquake were to actually hit, the displacement of level X would be much higher than delta sub XE because the V does not represent the force that will actually be induced in the structure by the earthquake. Okay, that's what we are designing for. But the earthquake probably will induce more forces and definitely more displacements. The C sub D, called deflection amplification factor, takes us from the elastically computed displacements to estimated design earthquake displacements. Delta sub x is equal to C sub D times delta sub xe. It is C sub D is not the difference between the two, okay, as one might get the impression from the figure. So delta sub xe amplified by C sub D gives us delta sub x, the estimated design earthquake displacements. Okay, so R C sub D, omega sub 0 is so the two things we talked about, R and C sub D, are at the system level for the whole structure. Omega sub 0, no matter what you see or read, it's even codes are sometimes kind of sloppy that way. Omega sub 0, we use at the member level. Let us say the analysis that produced delta sub xe, the elastic analysis of the structure under code prescribed seismic forces, gives us a bending moment of 100 foot gips at the support section of a beam. Okay, so at the support section of one beam, we calculate a bending moment of 100 foot gips negative under the design earthquake forces. If we want to figure out the largest bending moment that can be developed at this section, if the design earthquake were actually to hit, our estimate of that maximum moment would be omega sub 0 times the 100 foot gips negative. Okay? So if omega sub 0 is 3, as it is for special moment frames, then when we elastically compute a bending moment of 100 foot gips at a beam support section, the actual bending moment that can happen there is 300 foot gips. That's what omega sub 0 is about. It gives us an estimate of the largest internal force that can develop at a particular section under the design earthquake displacements. Okay, so R omega sub 0 C sub D. The R value, if you like, there are two kind of anchor values of R. Initially, those two values were set, and then pretty much all the other values were by comparison with those two kind of benchmark systems. That was in the early days, and now there is a lot more complication and some sophistication to it, but that's immaterial. It gives you an idea of the R values that we typically are dealing with. The R is 5 for a bearing wall system, and I defined it for you the other day. It is a system where shear walls carry gravity loads as well as lateral loads. So R is 5 for a bearing wall system with special reinforced concrete or reinforced masonry shear walls. That is kind of a benchmark value. And R is 8 for special moment frames of steel or concrete. That is another benchmark value. The other values were initially assigned by comparison with these two systems. Is the system more comparable to moment frames than a masonry bearing wall system? Is it less deformable than a masonry bearing wall system, and so forth. Okay? So those are kind of benchmark values. The seismic force resisting structural systems, I spent quite a bit of time on the other day, so I assume that this was understood and remembered. We have moment resisting frame system, bearing wall system, and then combination shear wall frame systems, which can be designed as dual systems or building frame systems. Okay. Now, this is portion of the R values table, table 12.2-1 of AC7, which is BNBC table 6.2.19. Okay. So we have the basic seismic force resisting system. The detailing reference you could actually ignore. Almost for all concrete systems, the reference is 14.2. Section 14.2 of AC7 simply references ACI 318. So the detailing rules are to be found in ACI 318, and those rules I will discuss with you starting tomorrow, actually. Okay. Then the R, omega sub 0, C sub D, and then there are height limits on almost all structural systems, with the exception of special moment frames of concrete and steel and dual systems utilizing special moment frames. Those are the only systems without height limits on them. Every other system has height limit on it, and most of the time the height limits are in the higher design categories, not so much on B. Design categories E and F, I have mentioned repeatedly, do not exist in Bangladesh. Okay. So special moment frame of concrete, R value of 8 has been mentioned, omega sub 0 of 3 has been mentioned, C sub D is 5.5. No height limit in any seismic design category. You go down to intermediate moment frame, R value becomes 5. Omega sub 0 remains 3, C sub D is now 4.5. Now, this is not permitted in design category D and above, not permitted. NL is no height limit, NP is not permitted. Ordinary moment frame, R value goes down to 3. The detailing is now much cruder. The omega sub 0 remains at 3, C sub D is now 2.5. No height limit in B, but it is not permitted even in C. Okay, and then I have listed here dual systems featuring special moment frames. So dual system, remember, has frames and shear walls. The frames are special moment frames. If the shear walls are special reinforced concrete shear walls, then you have your R value. If the shear walls are ordinary reinforced concrete shear walls, this is your R value. There are dual systems with intermediate moment frames also. The frame part is intermediate moment frame. Those can be with special reinforced concrete shear walls or ordinary reinforced concrete shear walls. You see the R values. Then bearing wall systems, I have listed the R values in AC7, special reinforced concrete shear walls, the 5 that I pointed out. Ordinary reinforced concrete shear wall, it goes down to 4. Anyway, it's a much more extensive table. The bearing wall system, some of the concrete systems are listed, and building frame system, again, some of the concrete systems are listed. The special, a bearing wall system with special reinforced concrete shear walls, R is 5. A building frame system with special reinforced concrete shear wall, R is 6. Okay. The reason is, in a building frame system, the gravity loads are carried by frames, the lateral loads by shear walls. So the elements that carry shear walls do not carry gravity load. The elements that carry lateral loads resist lateral loads, do not resist gravity. In a bearing wall system, the same shear walls that resist lateral forces also carry gravity for us. That's the reason for the difference in R values. Combinations of structural systems, okay, that happens fairly often. We combine frames and whatever, the systems that I described or that are listed in table 12.2-1, multiple systems may be combined in one structure. So the first is horizontal combination of structural systems in the same horizontal direction, okay, where different seismic force resisting systems are used in combination to resist seismic forces in the same direction, unless it is a dual system. The value of R used for design in that direction shall not be greater than the least value of R or of any of the systems utilized in that direction. Okay, so you string together 3 or 4 different structural systems. The R value will be the least R value for any of those 3 or 4 systems. The C sub D in the direction under consideration in any story shall not be less than the largest value of this factor for the R factor used in the same direction being considered. This is complicated language. We are essentially saying the C sub D, so R will be the smallest R value of the different systems that are strung together. C sub D shall be the corresponding C sub D. Like if the smallest R value of pipe comes from a bearing wall system, the corresponding C sub D of 2.5 will pipe will be the C sub D of the combination. Now, where do we say the largest value of this factor for the R factor used? Because there may be more than one system with the same R value in the combination. There may very well be more than one structural system that have the same R values. In that case, you shall take the larger C sub D or the largest C sub D for that same R value. If you have 3 systems strung together that have the same R value, but the C sub Ds are different, you will take the largest C sub D. Okay, so this is a little bit of a tricky language. Different systems in different horizontal directions. So something like this. Let me skip the language. Okay, this picture is good. So you have frames in one direction, shear walls in the other direction. Let us say these are special moment frames, and these are shear walls featuring special special shear walls. Bearing wall system featuring special shear walls. The 2 directions are designed for their respective R omega sub 0 and C sub D. There is no interaction. Okay? At one time there used to be, but for a long time we have gone by what is shown in the picture. So in the bearing wall direction, we have R of 5, C sub D of 5, omega sub 0 of 2.5. In the frame direction, we have R of 8, C sub D of 5.5, omega sub 0 of 3. Very simple. Okay, the 2 orthogonal directions are independent of each other. Okay, the vertical combination of structural systems gets a little complicated. I didn't go there to save on time, but you can read up, or if you ask me, we will discuss that. Okay. The importance factor I is 1.0 for risk category 2. It is, in your case, it is not risk category, it's occupancy category. I didn't notice that. However many times I go through the slide sets, this always happens, and this always bothers me. Anyway, occupancy category 2, which is standard occupancy, office buildings, apartment buildings, I is 1. The unimportant structures, occupancy category 1, the importance factor is also equal to 1. There is no importance factor smaller than 1. 3, which would be essentially assembly buildings where a lot of people congregate in one space in one time, I is 1.25. And then 4, essential facilities, hazardous facilities, I is 1.5. Now that gives us everything that goes into the design base shear equation. Okay. Having calculated the design base shear, we will, as I said, distribute it along the height of the structure in the manner prescribed by the code. Here is that distribution. Okay. The lateral force at floor level X, which is denoted by capital F sub X, is a coefficient times the design base shear V, and the coefficient is given by this equation. Okay. W sub X is the seismic weight at floor level X. H sub X is the height of floor level X above the base. K is 1 for periods up to half a second. Sorry. K is 1 for periods up to half a second. K is 2. So K of 1 is a linear distribution. Okay. Triangular distribution, whatever you like, going from 0 at the base to a maximum at the top. So for short period structures, we do a triangular distribution of the design base shear. K of 2 is a parabolic distribution going from 0 at the base to a maximum at the top. So for long period structures, period exceeding 2.5 seconds, we do a parabolic distribution of the design base shear. For K values, for period values between half a second and 2.5 seconds, which is a lot of structures, we do a linear distribution between a linear and a parabolic distribution. Or you can always take K of 2 and do a parabolic distribution. That is allowed by the code, but that does not make any sense. That way, if you take that option, you are dumping more of the lateral load towards the top of the structure, thereby getting larger overturning moment for the same base shear, which is essentially penalizing your client for no reason at all. So at this day and age, the interpolation between 1 and 2, K value of something like 1.37 should not be a problem for anybody. So I would suggest that you do that. If you have a period of, I don't know, 1.2 second, you interpolate between K of 1 and K of 2, and whatever your K value is, 1.37, you put that into that equation and do your distribution. Once you have distributed V, you don't have the base shear in the picture anymore. What you have are those F sub X forces at the various floor levels. Quite often, we look at and talk about the story shear V sub X. The story shear here in this top story is the top force F sub N. The story shear here is the sum of the top two forces. The story shear here is the sum of the three forces above. So the story shear at floor level X, or the story X, is summation of all the shears above. Okay, and that is denoted, that is kind of expressed by that expression. So at the in the bottom story, the story shear is the sum of all the F sub x forces, which is the same as the base shear. Okay, so this level, the base shear is F sub, the story shear is F sub n. At this level, the story shear is equal to base shear. Okay, that is vertical distribution of the base shear. Once we have our vertical distribution and we can calculate the story shear in a particular story, how is that distributed among the seismic force resisting systems? So this is a hypothetical building. We have story shear V sub x in story x. Story x or the building has 2 frames in the up and down direction and 3 shear walls of unequal length. How is V sub x distributed among the 5 seismic force resisting systems, the 2 frames and the 3 shear walls? The answer is in proportion to the relative lateral rigidities of the seismic force resisting elements. If it takes 1 unit of force to impart unit interstory displacement to the frames, it takes 2 units of force to impart 1 unit of interstory drift to this shear wall. It takes 3 units of force to do the same thing to this shear wall and 4 units of force to impart unit interstory drift to that shear wall. Then the 2 frames will get 1 share of V sub x, like each of the 2 frames will get 1 share of V sub x. This will get 2 shares, this will get 3 shares, this will get 4 shares. Okay, so in proportion to the relative lateral rigidities. Now what I said is true. If the diaphragm is rigid, if the diaphragm does not deflect too much in its own plane. Rigid versus flexible diaphragm I will discuss on a subsequent occasion, not today, but it is very easy to understand what rigid versus flexible is. Diaphragm bends in its own plane, and if as a result of this bending it does not deflect much, it is a rigid diaphragm. If it deflects a lot, it's a flexible diaphragm. Okay, so if the diaphragm is rigid, which should be most of the time the case, the lateral force distribution will be as I indicated. If, on the other hand, the diaphragm is flexible, then the story shear is distributed to the lateral force resisting systems in proportion to the tributary areas, not the relative lateral rigidities. Now, there is the complication of torsion. The story shear that we have been talking about acts through the center of mass. In this picture, although the 3 shear walls are of unequal length, I have indicated that the center of mass is pretty much located at the centroid because the masses of a building are mostly at the floor levels and the roof level. The shear walls and columns account for very little of the mass. So the fact that the left shear wall is so much longer than the right shear wall does not move the center of mass all that much to the left of the centroid. It is a very different story when we talk about the center of rigidity. The rigidity of this shear wall is way more than that of this shear wall. It is proportional to the cube of the length. So the center of rigidity is definitely towards the left of the centroid. Okay. Now the story shear acts through the center of mass. the resistance to the story shear acts through the center of rigidity. And that since there is an eccentricity between the two, that causes torsion. The force acts along this direction, along this line. The resistance acts along that line. So there is a torsion which will add to the shears in these resisting elements and will take away from the shears in those resisting elements. The addition we always consider in design, that take away we kind of ignore. Okay, so this is the significance of torsion. The picture is simplified in the sense that torsion will not only go to these elements in the up and down direction. Some of the torsion will be resisted by those frames, and that I did not indicate in the figure. So it's kind of a simplistic figure, but the point I'm trying to make is made with that figure. So torsional moment due to difference in location of center of mass and center of rigidity must be considered for rigid diaphragms. Now, when the center of mass and the center of rigidity coincide, and there is no actual torsion, which is now called inherent torsion, we still consider an accidental torsion if our diaphragm is rigid. And the accidental torsion is the story shear multiplied by 5% of the plane dimension perpendicular to the story shear. Okay, so accidental torsion is the story shear multiplied by 5% of the plane dimension perpendicular to the story shear. Now, there was a time, a long time ago, when we used to design for the actual torsion subject to a minimum of the accidental torsion. But those days are long gone, long gone. We have for a long time been designing for the actual torsion plus the accidental torsion. Actual torsion plus the accidental torsion. Not only that, the accidental torsion many times has to be amplified. For structures assigned to design category CD, you don't have EF, where type 1A or 1B irregularity exists. That's torsional and extreme torsional. ASC 705 section such and such requires that the torsional and accidental torsional moments be amplified by a torsional amplification factor that can be up to 3. Okay, so you design for actual torsion plus accidental torsion, and if your structure is torsionally irregular or extreme torsionally irregular, then you design for the actual torsion and the accidental torsion amplified by the accidental torsion amplification factor, this A sub x. Delta maximum is the maximum lateral deflection of the lateral force resisting system. Delta average is the average lateral displacement. Anyway, so this expression is pretty simple. And you will see a lot of this delta maximum and delta average in the next segment on irregular structures. So it will be very clear what A sub x is. It can be up to 3. Overturning moment is simply the forces at the various flow levels multiplied by their height. If we are looking at overturning moment at the base, the overturning moment are the forces at the various flow levels multiplied by their heights above the base, as simple as that. Okay. Now, the foundations of structures, except inverted pendulum type structures. This is like a water tank where all the mass is at the top. The foundations of structures, except inverted pendulum structures, shall be permitted to be designed for 3/4 of the foundation overturning design moment M sub 0 determined using. So this is a fairly significant break that you get. Foundation design does not have to be for the overturning moment at the base. at the soil foundation interface, you can take a 25% discount on that. Okay, and this is in AC 705 as well, section 1213.4. This discount for foundation design. Okay, that brings us to a major topic. One of the last. This is not the last in seismic in the equivalent lateral force procedure, and some of these things extend beyond the procedure. Uh, in seismic design, we have drift check. The interstory drift, and I'll define it in a second, shall be within tolerable limits. Seismic design in our codes is essentially about life safety. Occupants will at least be able to escape before a structure actually collapses. That is pretty much our aim. We are not trying to minimize, we are not trying definitely to prevent damage to our structure or anything like that. Now, there are two exceptions to what I just said. Yes, our codes are life safety codes, but in two situations, we seem to go beyond life safety. One is where we impose a limit on interstory drift. That is more than life safety. We are now trying to prevent damage to non-structural elements or minimize damage to non-structural elements. We are trying to keep machinery that is mounted on our floors functioning. Okay, so the drift check has to do with controlling property damage and to make it more likely that the structure will go on functioning during and following an earthquake. This is beyond life safety. The other place where we go beyond strict life safety is when we include an importance factor larger than one in design. That also takes us in the same direction of damage control and continued functioning of the structure during and following an earthquake. Now, drift check starts with the analysis I have been talking about. The design base shear V distributed along the height of the structure in the manner prescribed by the code. These are the F sub X forces. We do elastic analysis of our structure under those forces. The deflection at floor level X is lowercase delta sub X E for elastically computed. X is for floor level X, E for elastically computed. The same deflection also, the same analysis also gives us Q sub E, which are the internal forces at the various critical sections of the various structural members. The bending moment at the support section of a beam is Q sub E. The shear force at the same section of the beam is Q sub E. The axial force in a column is Q sub E. So Q sub E is generic notation for the internal forces caused at the various critical sections of the various structural members by the code prescribed seismic forces. Okay, so delta sub Xe and Q sub E. The delta sub Xe multiplied by C sub D gives us the estimated design earthquake displacement, as I mentioned. Okay, so delta sub X is C sub D times delta sub Xc, but it is a little bit more than that. in delta sub x, we divide C sub D delta sub xc by the importance factor I. We do that because we are going to check the interstory drift under drift limits. And the drift limits are a function of the occupancy of the structure. The drift limit for a hospital is half that for an office building. And we should not penalize a hospital twice, once by instituting a tighter drift limit, and the second time by using an I factor of 1, and thereby increasing the forces under which we are calculating the drifts. Okay, so we take I out of the picture. Delta sub x is C sub D times delta sub xc divided by I. That delta sub x at the top of a story minus the same delta sub x at the bottom of the same story is the interstory drift. So this is delta sub x at the top of a story minus delta sub x at the bottom of the same story. That is delta sub x, the interstory drift in story x. That has to be less than or equal to the allowable story drift delta sub a. The delta sub a is given, the notation you know. The delta sub a is given in this table 12.12.1 of AC7, table 6-21 in BNBC 2020. Most of the time you'll be in this line, all other buildings. And your drift limits will be the interstory drift shall not exceed 2% of story height for risk category 1 or 2 buildings, standard occupancy buildings or miscellaneous occupancy, shall not exceed 1.5 story height for schools, let us say assembly buildings, and shall not exceed 1% of story height for hospitals, police stations, fire stations, all essential facilities. Okay. The last topic, I am way behind. I mean, it's approaching 1 hour and I'm not done with what was supposed to be yesterday. So what will happen to today's segment, I don't quite know yet. We'll see. The time problem is just a problem, but we have to cover the material. Okay, the strength design load combinations I discussed at length. One of these days, the days have gotten mixed up. These are the strength design load combinations of AC 705 and BNBC 2020. These are the same load combinations where we have eliminated the F, the fluid pressure, the horizontal earth pressure H, and the temperature effect T. So these are the strength design load combinations of the code. 2 of the load combinations have earthquake effect E in them. This is, I call this the additive seismic load combination. The gravity causes negative bending moment at a support section. Earthquake also causes negative bending moment. If we want to figure out the largest negative bending moment at that section, we will use that load combination. Gravity adds to the effects of earthquakes. This is the counteractive load combination. Gravity still causes negative bending moment at our support section, but earthquake causes positive bending moment because earthquake has changed direction. If we want to calculate the smallest negative or the largest positive bending moment at the section, we will use this load combination, 0.9 dead plus 1.0 E. Now, E in AC7, first of all, and I'll talk about BNBC in a second. In AC7, the earthquake effect E is made up of horizontal earthquake effect and vertical earthquake effect. The horizontal earthquake effect is the Q sub E that I showed you. This is the internal forces obtained by analysis of the structure, elastic analysis of the structure under code prescribed seismic forces. So Q sub E multiplied by the redundancy factor rho, which is 1 or 1.3. Rho is 1 for redundant structures, 1.3 for non-redundant structures. The vertical earthquake effect is 20% of the short period design spectral acceleration, which you are familiar with by now, and D, the design dead load. Okay. In BNBC 2020, there is no rho. The subject of redundancy is mentioned in one paragraph, but there is no redundancy factor in BNBC 2020. And this is one of many major topics that are simply not covered. Okay, and I will devote one lecture to those things. And the point to S sub ds times d is essentially written differently. It is exactly the same. So in BNBC 2020, the E is Q sub E plus 0.2 S sub ds times d, or in the additive seismic load combination, in the counteractive load combination, it is Q sub E minus 0.2 S sub ds times d. Okay. In AC7, rho is 1 for seismic design categories A, B, and C. In design categories D, E, and F, it can be 1 or 1.3, as I mentioned already. Okay. I don't know why this picture came again. Okay. So BNBC, I mentioned that rho is 1. E sub B is written that way, and I have explained why that is exactly equal to that. I wouldn't spend time on the details. It's very clearly spelled out. So in the additive load combination, when we write E is equal to Q sub E plus 0.2 S sub ds times D, and we collect terms, what we have done is we have increased the dead load factor from 1.2 to 1.2 plus 0.2 S sub ds. Say if S sub ds is equal to 1, we have made the dead load factor 1.4 by considering vertically downward earthquake forces. Okay. If you take the example of Dhaka, which is zone 2, soil type S sub D is quite common, particularly on the north side. S sub ds then is 0.45. This value is given in Appendix C. For S sub ds of 0.45, 0.2 S sub ds is 0.09, and the dead load factor becomes 1.29, as you see here. So in Dhaka, seismic design category D structure shall be designed for this load combination. Okay. I don't know why I said seismic design category D structure. Structure shall be designed for this load combination. The load factor on live load, I have mentioned repeatedly before, is 0.5 unless you are designing a parking structure, a place of public assembly, or an area supporting more than 100 pounds per square foot of live load. That's what is said here. The counteractive load combination E is written as Q sub E minus 0.2 S sub ds times D, indicating vertically upward earthquake ground motion. Now the dead load factor is decreased from 0.9 to minus, from 0.9 to 0.9 minus 0.2 S sub ds times D. So for Dhaka, where S sub ds is 0.45, 0.2 times that is 0.09, the dead load factor is 0.9 minus 0.09, which is 0.81. Okay, so that is the counteractive seismic load combination for Dhaka on soil type SD. Okay, The pretty much the final topic before I go to today's session. There are the regular load combinations that we saw, and then there are load combinations with overstrength factor, as they are called, in AC7 as well as BNBC 2020. Overstrength factor, load combinations with overstrength factor. The first and foremost and most important thing I am going to tell you about the load combinations with overstrength factor is they must be used where required by AC7 or BNBC 2020, but more importantly, they must not be used where not required by the code. You cannot just willy-nilly use them at your whim. You cannot. That will be to the detriment of your structure. So these load combinations with overstrength factor shall be used where required and shall not be used where not required. The second part is more important than the first part, I would say. Okay, please do not use them where they're not required. In AC7, there are only three places where they're required. In the IBC, there are a couple more places. BNBC has 3 or 4 places that I'll show you where they're required. Do not use them elsewhere. Okay. AC7 requires the load combinations with overstrength factor to be used in this particular section, and this is how it reads. Foundation and other elements used to provide overturning resistance at the base of cantilever column elements shall have the strength to resist the load combination with overstrength factor, etc. So cantilever wall systems are where a cantilever column offers or resists the entire seismic forces. It doesn't have to be one column, it can be a series of columns, but those are cantilever columns comprising the entire seismic force resisting system. The entire seismic resistance comes from the connection of the frame to the foundation, of the column to the foundation. And so that foundation and other elements used to provide overturning resistance must be designed using the load combination with overstrength factor. This particular requirement is not in BNBC, probably because you do not use this system, at least not much. The second, by far the most important place where you need to use load combination with overstrength factor is columns supporting discontinued shear walls. That is a simplistic way of saying, actually the code says structural members supporting stiffer elements or something like that, more generic. Elements supporting discontinuous walls or frames. That's the language in AC7. Okay. So these are very, very common around the world, actually. Many parts of the world, the residents of apartment buildings park their cars underneath the building. So the lowest level is open, supported by columns. But then from the next level, you have shear walls, because those are residential units and walls are needed to separate the different spaces, bedrooms and so forth. So this is extremely common, but this also gives you what are called soft stories. The bottom story is laterally much less stiff than the upper levels. And so in an earthquake, the inelastic deformations will be concentrated in the lowest level, and those columns will be very vulnerable to damage. Okay, so those columns must be designed using load combinations with overstrength factor. We must make them stronger. And there are other things we do to the same columns. This is the famous Olive View Hospital after the 1971 San Fernando earthquake. I showed you a picture the other day where the ambulances were pinned down by the canopy that had fallen on them. This is a this is a side face of the building or whatever. So the these columns are supporting steep shear walls above, as you can see very clearly. The only reason the building is standing up is that, for reasons unknown to me, the central columns were spirally reinforced with very tight pitch to the spiral. So those columns were inelastically deformable and are holding the building up. These columns, this is typical of pre-1973 UBC construction. Plenty of longitudinal steel, no transverse reinforcement or very little. So those columns have completely failed as they are expected to. Today's design, those columns, all four columns, will be designed for overstrength using load combinations with overstrength factor, and the entire length of that column will be detailed for ductility. We will have special detailing. Okay, so we do both of those things, and so in two different ways, those columns supporting discontinued shear walls are much superior to what we used to build before 1973. The third place where ASC7 requires us to use load combinations with overstrength factor are collector elements of diaphragms. Okay. Now let us explain that. So this is a slab acting as a diaphragm. A slab acted upon bilateral loads which will cause in-plane bending. So you are looking at compression on this face, tension on that face, and shears along the side faces. Those shears have to be transferred to supporting elements, shear walls or frames. Now, if that shear wall were supporting the entire edge of the diaphragm, there would be no collector. But we have a situation where we have a 50-foot diaphragm edge and only 20 feet of shear walls. What happens now? You have to have something, a beam or at least a bunch of reinforcing bars that will collect the shear and then deliver them to the shear wall. And that element, the bunch of reinforcing bars or the beam, is a collecting element. They are collecting the shears and delivering them to the lateral, the seismic force resisting shear wall. Okay. So when you have this situation, a shear wall or a frame supporting only part of a diaphragm edge, not all of it, we have collector elements. There are other situations where the same thing exists. Anyway, those collector elements must be designed using the load combinations with overstrength factor. This is extremely important. To make the point, this is a parking structure after the Northridge earthquake of, when was it? 90, years got mixed up, 94, I believe. This is the Northridge Fashion Center, as they used to call it, the shopping center close to the earthquake epicenter. This was one of a number of precast parking structures that did not do well, as you can see. So the parking structure is largely down on the ground. But as we approached the building, this shear wall looked really incredibly good. It not only was standing up, pretty much nothing had happened to it, not even significant cracking. And the question immediately arose, how come the rest of the structure is doing so badly and the shear wall is so much better off? And the answer that emerged pretty quickly is that the shear walls didn't have to do anything during the earthquake. And when you don't have to do anything, it's easy to look good. The shear walls didn't have to do anything because the collector elements that were supposed to deliver the shear to the shear walls failed before the delivery took place. So from that point on, this was 94, 97 UBC, we already required collector elements to be designed using what we used to call special seismic load combinations back in those days. So this is vitally important, collector elements to be designed using the load combinations with overstrain factor. So these are the special seismic load combinations or load combinations with overstrain factor as we call them now. Okay. So this is the same as the regular load combinations, except here we have omega sub 0 rather than the rho, the redundancy factor. The redundancy factor, you remember, is 1 or 1.3 if your seismic design category is D, E, or F. Omega sub 0, on the other hand, is given in the R values table. And if you look at the table, the number is 2, 2.5, or 3. So we are amplifying the effect of design-based shear by a much larger multiplier and then adding to gravity effects. So this is the difference between regular seismic load combinations and the load combinations with overstrain factor. Okay. Where does the BNBC require you to use special seismic load combinations? As I said, the cantilever column base is not there, but elements supporting discontinuous wall subframes is very much there. I will not read the text. The important thing is it's there. Then this talks about uh, collector elements in a roundabout way. There is a 25%. Anyway, all of this will come up. Uh, I can't remember now. I think maybe in the next segment we will discuss what is said here, but not now. This is telling you that the collector elements, in a roundabout way, you'll be very confused if you read it, but it is essentially telling you to design the collector elements using the load combinations with overstrain factor. Uh, Actually, this is much more so. 225, this section I will discuss later, and when I do, I will refer back to the section of BNBC. I will tell you that this is what I kind of skipped. This tells you to design the collector elements using load combinations with overstrain factor. And then something that is not in ASC 7, it is in the IBC, batter piles, which are inclined piles. Batter piles and their connections shall be capable of resisting forces and moments from the load combinations with overstrain factor. So batter piles you shall also design using load combinations with overstrain factor. Okay, so that is now the end of what I was supposed to do yesterday. And since we are going to take a break at some point, we will do it now a little early before I switch to. So it is 14 after by my watch. So we'll come back at 19 after and start with the next segment. Okay. And then I don't know how the time will work, but I'll take questions at some point. Okay, I think it is time. I hope you can see my screen. I did tell you yesterday to be prepared to run a bit late. Uh, I do not know what we'll see. I'll start and see where it goes. I feel really bad that it's tough not only on you but on your families, your spouses and children, day after day, the entire evening. At the same time, I do not know that there was another way of delivering so much training that is so intense. I think this is a lot better than you're having to come to the institution of engineers after work and going back home at midnight. So at least compared to that, this is better. It is just a whole lot of training crammed into relatively short period of time. But once this is all absorbed, I think you will benefit quite a bit. That's at least our hope. So we will go into a discussion of building configuration and structural irregularities. This is again a not a short presentation, but let me see if I can make it a little. Yeah. Anyway, so this is what we will look at in this segment: earthquake experiences with irregular structures, horizontal structural irregularities that came up in discussion yesterday, vertical structural irregularities. I showed you the lists from BNBC, which are the same as from ASC 7. And in this segment, all references are to ASC 710 rather than O5. 10 was adopted by 2012 and 2015 IBC. I did that because there were some beneficial changes or clarifications made in AC 710. It's not very different from AC 705, but a couple of things were improved. So I thought that it was preferable. Configuration, the word means a relative arrangement of parts, something produced by such arrangement. This is dictionary meaning. Relative arrangement of parts, something produced by such arrangement. In the structural design we do, the plan configuration of a structure and the vertical configuration of a structure, how a structure is put together in the horizontal direction and how it is put together in the vertical direction, both matter. Both become pretty important. So we consider both. The configuration of a structure can significantly affect its performance during a strong earthquake that produces the ground motion contemplated in the IBC and AC 7, same as BNBC 2020. Okay. And the picture shows the Ministry of Transportation and Telecommunication, Mexico City. I showed you the picture the other day. This was in the wrong height range, so it was kind of resonant response, but the L shape of the building did not help. That meant a lot of torsion, which always hurts. ASC7 seismic design provisions were developed basically for regular buildings. This is something we need to understand. Okay, everything was developed basically for regular buildings. Past earthquakes have repeatedly shown that irregular buildings suffer greater damage, incomparably greater damage sometimes than regular buildings. This happens even with good design and construction. It is the configuration is the problem. It is not the design and the construction. By proper design and proper construction, you can improve things, but the problem remains. Okay, So irregular buildings attract more damage to themselves. Some examples: the so-called Loma Prieta earthquake of 1989. This was the San Francisco area earthquake, the last significant one in the San Francisco area, magnitude 7.1. Okay. What we saw in that earthquake, this is the Marina District as it is called. This was built on fill, and these buildings, when they were built, there were no automobiles, so there were no garages. When cars came, people got openings in the ground story to have garages. Okay, so the garages were created by uh, removing walls after the buildings had been constructed, and that produced sob stories. And these buildings with sob stories did not do well at all in the Loma Prieta earthquake, as you would imagine. So the irregularity was the problem. You see a closer up view of one of the buildings. You see what has happened, and you see the garage door. And anyway, so I think the titles say Marina District, a stiffness issue, sob story. This is the San Fernando earthquake that you keep on hearing about, 1971. This is the building that I just showed you. I showed you the other face, the left face. These are the ambulances that were pinned by the this canopy fell on the ambulances. But I just showed you this picture. The problem was the sob story, the column supporting the discontinued shear walls. If the columns had been designed properly and detailed properly, the building probably would have stood up. That's besides the point. The point is that the irregularity poses a challenge. It causes a problem that has to be addressed. Philippine earthquake, 19. This is Manila, 1976. This kind of a building is very common again around the world. It is at the corner of two streets. The street faces of the building are open. There are no walls. You don't want walls. You want exposure to the outside. You want to see outside. You want outside people to see you, your stores and whatever. So the two back faces have walls. The two front faces do not have walls, which mean a lot of torsion. So the shear walls being stiffer will attract the earthquake forces. The earthquake forces will fail the shear walls, and then the when the shear walls fail, the forces will be carried by the columns, and then they will fail, and this will be the result. This building has lost one story. If you are standing here, one full story of the building is gone. Mexico earthquake, 1985. The earthquake, which earthquake is incidental? The building. This is even worse. This is a triangular building. So only the back face has walls. The other two faces do not have walls. They are much more flexible. And the resulting torsion causes a lot of problems of this for these buildings. You can design against it, but the problem the problem is very real. In a regular structure, inelastic demands produced by strong ground shaking tend to be well distributed throughout the structure, resulting in a dispersion of energy dissipation and damage. That is very key thing to understand. Okay, in a regular structure, inelastic demands produced by strong ground shaking tend to be well distributed throughout the structure, resulting in a dispersion of energy dissipation and damage. In irregular structures, inelastic behavior can concentrate in the zone of irregularity, resulting in a rapid failure of structural elements in these areas. This is the difference between regular and irregular buildings. Some irregularities introduce unanticipated stresses into the structure, which designers frequently overlook when detailing the structural system. This is a building out of Japan, I believe, after the Kobe earthquake. That's where I think I took that picture. Uh, so reasons for poor seismic performance of irregular structures. Elastic analysis methods, which is what we almost always use as basis of design. Whether it is static or dynamic doesn't make any difference. Elastic analysis methods typically employed in structural design often cannot predict the distribution of earthquake demands in an irregular structure very well, leading to inadequate design in the zone of irregularity. The building with the two open faces and two back faces with walls that I mentioned. When the shear wall is damaged, the structural behavior is not regular anymore. So how would you find out from elastic analysis what is happening subsequently to the shear walls and more importantly to the columns? You cannot, there is no way you can figure out the actual force distribution after the behavior of the structure has become inelastic. The code regulations concerning irregular structures were introduced in 1988 edition of the Uniform Building Code. The types of irregularities that you see, these date back to then. There have been a couple of modifications, but only a couple. This has been a very stable part of the code. The thrust of the regulations is to encourage that buildings be designed to have regular configurations. The idea is not to penalize the lack of regularity, but to encourage regular configurations. Important feature is prohibition of gross irregularity in buildings located on sites close to major faults where very strong ground motion and extreme inelastic demands can be experienced. So there are sometimes downright prohibition. You cannot build irregular structures close to a major fault that can generate large earthquake ground motion. So you have seen this list yesterday. Horizontal irregularities, torsional, extreme torsional, which was introduced in 2000 IBC, that was not in 1988 UBC. Re-entrant corner, diaphragm discontinuity, out of plane offset, non-parallel system. The way AC7 handles it, we have definitions, and then there is a table that tells you if you have, let us say, torsional irregularity, then which particular sections of AC7 get triggered. So if you have torsional irregularity, the table will tell you, go to the section that has restrictions on analysis procedures. And when you go there, you will see that you have to do dynamic analysis. The static analysis will not do, for instance. Okay, so I want to take you through basically all of that. Okay, what is the definition, and what does AC7 ask you to tell you if you have that particular type of irregularity. The vertical irregularities are stiffness, extreme stiffness, soft story, extreme soft story, weight irregularity, vertical geometric, in-plane discontinuity, discontinuity in lateral strength or weak story, and then extreme weak story. In our seismic design code master, I wanted to show how much space we have devoted to this topic of irregular structures. It is that important. Okay. So we will start with the very first type 1A, torsional irregularity, and look at the definition and also what AC7 requires us to do when we have torsional irregularity. Okay. So definition. This is the undeformed structure. This is the structure after the earthquake has uh, caused displacements and so forth. The maximum displacement is at this corner, and it is denoted by delta maximum. And delta average is the average displacement of this corner and that corner. If the maximum is less than or equal to 120% of the average, we don't have any torsional irregularity. Okay, it is considered a regular structure. If the maximum is between 120 and 140% of the average displacement, then we have torsional irregularity type 1A. If the delta maximum is larger than 140% of delta average, we have extreme torsional irregularity. Okay, so we have defined torsional irregularity 1A and extreme torsional irregularity 1B with this one picture. Okay, so up to 1.2, no irregularity. Between 1.2 and 1.4, we have type 1A. Above 1.4, we have type 1B. Okay. Same thing, L-shaped building, the same idea. Delta A is now the maximum, and the average is delta A plus delta B by 2. If this is true, then we have type 1A irregularity as shown in this picture. Okay. If we have 1A irregularity, then those are the provisions of ASC7 that get triggered. We have to abide by all of those requirements. Okay. The requirements sometimes apply to, not all of them are for all seismic design categories. This requirement applies in seismic design categories D through F. This one, however, B through F. So that column is kind of important. Now here comes the long paragraph in BNBC. Before we discussed when we were discussing collectors having to be designed for load combinations using overstrain factor, there was a paragraph that I said will come up later, and this is now that later. Okay, so this says 25% increase in seismic forces in connections in diaphragms and collectors. Okay, there is somewhere else where you will get more elaboration on that. I don't remember now. It is all mixed up. I have 7 or 8 seismic segments I was preparing. Anyway, what is where I am not exactly sure of now, but you will get more details on this. 25% increase in seismic forces in connections in diaphragms and collectors. It requires more detail. I'll provide more detail. Maybe it is coming up. I think it is coming right up. Yeah. the permitted analytical procedure. Let us go one by one. I think I have elaboration on everything. So the first one, let us look at the details. I think it is right here. Okay, D through F. So this is the section. 12334 is the section that we are being asked to go to if we have torsional irregularity type 1A. So this is in detail. For structures assigned to seismic design category D or F and having a horizontal structural irregularity 1A, 1B, 2, re-entrant corner, 3, diaphragm discontinuity, 4, out of plane offset, or vertical type force. So many times this section will be invoked. The design forces determined from section 1210.11 shall be increased 25% for the following elements of the seismic force resisting system. Okay, this is what I wanted you to see. So where do you have to increase the design forces by 25%? Connections of diaphragms to vertical elements and collectors. So let me, the very nice picture. This was in the previous segment. Do you remember the picture of the diaphragm that I showed to explain what collectors are? So the diaphragm is connected to the collector where there is no shear wall. The diaphragm is connected to the shear wall where there is a shear wall. Connections of diaphragms to vertical elements, meaning shear walls or frames, and to collectors. Those connections have to be designed for 25% more forces. And then collectors, the collectors themselves, and their connections, including connections to vertical elements of the seismic force resisting system, the collector to shear wall connection. Now, there is a significant exception. Forces calculated using the seismic load effects, including overstrain factor. So when, if you are in design category D, the collectors and their connections have to be designed using the load combinations with overstrain factor. And in that case, the 25% requirement goes away. It is not on top of omega sub 0. Okay. So most of the time, at least that part of the requirement will be moved in design category D. Okay. The explanation of where the 25% increase applies. So this is a diaphragm. This is the structure. It happens to be a wooden structure. This is the shear wall. This part is the collector. Okay. This is elevation. This elevation. Okay. Here we cut a section here. We cut a section there. So this is the diaphragm to collector connection, A. This is the collector to shear wall connection. I'm sorry. This is the collector to shear wall connection. No, I'm sorry. This is diaphragm to collector connection. This is the collector to shear wall connection. And this is the diaphragm to shear wall connection. Okay, are you with me? This is diaphragm to collector connection. This is collector to shear wall connection. And this is the diaphragm to shear wall connection, A, B, and C. So A is diaphragm to collector connection, as shown in the picture. Okay, this is the collector, this is the diaphragm. The design forces have to be increased 25%. This is the collector to shear wall connection. So this connection, the forces have to be increased 25%. And this is the diaphragm to shear wall connection. This is the shear wall, this is the diaphragm. this connection has to be designed for 25% higher forces. Okay. Second thing you have to look at, if you go back to the table, and I won't go back every time, but first time. The next thing you have to look at is table 12.6-1, which is the permitted analytical procedures. Okay. We went over that yesterday. If you have torsional, if you have torsional irregularity 1A or 1B, that is one of the bad irregularities that will trigger dynamic analysis even for the shorter buildings. Okay, so if you have torsional irregularity, you have to look at this table and do dynamic analysis. Torsional modes of vibration may be excited whose effects may not be adequately represented by the equivalent lateral force procedure. You just saw that picture, explanation of torsion, and I had this page, the amplification of accident. So the first thing is 25% increase. Second thing you look at is that table permitted analytical procedure. The third thing is the amplification of accidental torsion. This is required for type 1A and 1B buildings. So this is another section that is triggered, 12843. So you have to design torsionally irregular buildings for the inherent torsion plus the accidental torsion amplified by the torsional amplification factor given here, and that factor can be up to 3. By now you know delta maximum and delta average very well. Okay, so this is just illustrating the delta maximum and delta average and the definition of the accidental torsion amplification factor, or the torsional amplification factor. I don't know why it's accidental. Okay. The next thing you have to look at, the next section that is triggered is 1286. And what this is if you don't have torsional irregularity, interstory drift. Interstory drift, remember, is deflection at the top of a story minus deflection at the bottom of the story. Now, typically, we calculate the deflection at the center of mass. And now, that is not good enough if you have significant torsion. So for structures assigned to design categories C, D, or F having horizontal irregularity 1A or 1B, which would indicate significant torsion, the design story drift shall be computed as the largest difference of deflections of vertically aligned points at the top and bottom of the story under consideration along any edges of the structure. When you have torsion, the torsion would, so normally interstory drift would be the deflection at the center of mass of the floor above and the center of mass of the floor below. But when there is torsion, you need to look at the periphery of the building. The, what is the word? Edges, the edges of the building. Okay, because torsion, the torsional deflections will be added to the translation caused by the earthquake, and the largest deflections are going to be along the periphery of the structure, along the edges. So we will have to look at the difference of deflections of vertically aligned points along the edges. Now, theoretically, you have to go around the edge, but with some experience, you kind of know where to take these vertically aligned points. But the point remains that you cannot go with the deflections at the center of mass anymore. Okay, so that was the entire table. Let me. So this is the same table. I'll go back. I'm not skipping. So we looked at the 25% increase, the permitted analytical procedure, 3D structural model required. This is nothing to elaborate on that. If you have torsion, you need 3D model. 2D simply doesn't do it. And that should be kind of intuitive. Amplification of accidental torsion, we talked about. Design story based on largest difference in deflection along the edges that we just talked about. The last item says that even when you do nonlinear time history analysis, you will have to do 3D. The 2D will not be sufficient anymore. Okay? We go from type 1A to type 1B. Now the maximum is more than 140% of average. This irregularity is prohibited in seismic design category E and F. You do not have that in Bangladesh, so you don't have to worry about it. But in near fault areas, this is simply not allowed to be built. The same restrictions apply, the same table. 1A and 1B, no difference. What you have to, the difference is that outright ban that you cannot do it in near fault areas, seismic design category E and F. This probably goes into a little too much detail in a supplement to ASC 710. AC 7 said that the redundancy factor rho shall be automatically taken equal to 1 for buildings with extreme, for structures assigned to seismic design category D and having extreme torsional irregularity, rho shall be 1.3. This is, I won't go beyond that. This goes into, and this is AC 710 supplement for you. It is in the future. Okay, re-entrant corners. Something that looks like this. Re-entrant corner exists when projection B, this distance, this projection B is larger than 15% of A. So look at A, look at B. If B is larger than 15% of A and D is larger than 15% of C, then you have re-entrant corner irregularity. So this is the definition, and these are the restrictions. The 25% increase in seismic forces in connections and diaphragms and permitted analytical procedure. If you have horizontal type 2, that is a bad irregularity, and you will have to do dynamic analysis even for shorter buildings. The re-entrant corner irregularity, why we are so careful with it, is re-entrant corners may form coupled wings which may respond in an opening and closing fashion. That is very easy to visualize. This may give rise to high stresses in the vicinity of the re-entrant corners. Diaphragm discontinuity irregularity. Diaphragm discontinuity exists when area of opening is larger than 50% of the opening of the area of the diaphragm. The area of the opening is larger than 50% of the area of the diaphragm, or effective diaphragm stiffness changes more than 50% from one story to the next. This effective stiffness is not defined. That makes it a bit of a problem. But anyway, significant change in diaphragm stiffness from one story to the next. This irregularity is not very well defined, and it has undergone changes in subsequent editions of ASC 7 that I cannot go into today. But in ASC 705, you will see exactly what you see here, no change from 5 to 10. AC 705 to AC 710. So 50% of the diaphragm is an opening, 50% or more, or effective diaphragm stiffness changes more than 50% from one story to the next. What you consider effective is up to you. If you have diaphragm discontinuity, the regulations that are triggered are again 25% increase in seismic forces and permitted analytical procedure. Diaphragm discontinuity, irregularity, continuing with our discussion. This is very, very common now in the US. A wood structure sitting on a concrete podium structure, as they are called. This concrete structure is not as stiff as they usually are, but the point is that this diaphragm is concrete. Those diaphragms are made of wood, and you definitely have more than 50% change in stiffness. So we are looking at this diaphragm discontinuity irregularity. These are questions that we got from wherever. If the roof diaphragm has an opening in it, which results in the stiffness of the second floor diaphragm being 50% stiffer than the roof, does that make it irregular? The plan irregularity definition says story to story. We said yes, it would be considered irregular. It doesn't matter whether floor or roof. The question and answer, I think I'm going to skip in view of our time situation. You can easily read them. And okay, and sometimes the context is probably a little too American, may not apply to you. The second question on which we have spent a lot of, because this is an important question here. In office buildings, the floors are typically steel. Well, first of all, many office buildings are made of steel, and the floors are steel decks that are topped with concrete. But the roof level steel deck is typically not topped. We're not going to do anything on the roof anyway, so there is no reason to put a concrete topping. So are all those buildings irregular? The untopped roof diaphragm is definitely much less stiff than the topped floor diaphragms. Are all those buildings irregular? And opinions are expressed that you can read. And that situation probably does not exist in Bangladesh, at least to a significant extent. So don't maybe worry too much about it. Next, type 4 is out of plane offset irregularity. And I think the pictures are quite clear. ASC 710 clarifies that at least one of the vertical elements has offset. So discontinuity in vertical elements of lateral force resisting system. Yeah. So this is a very graphic picture that comes from FEMA. And so this picture makes an important point. So this shear wall was coming down, but then it makes an offset and comes down a different line. Now this shear has an opposite shear at the base of the wall that will, so that shear will have to go from here to there through the diaphragm. Okay, So there will be this shear, there will be that shear, and then there will be shear in the diaphragm. The diaphragm shear, this is called a transfer diaphragm when this thing happens, when the diaphragm has to transfer the shear from the base of this wall to the top of the continuing wall. This transfer diaphragm has to be treated properly in design. Those transfer forces have to be treated properly. But anyway, this is out of plane offset irregularity. Uh, this is a nice looking building where you have a very significant offset of the seismic force resisting system. This wall was coming down, and I don't even know where it is continuing along this line or anyway. So there is discontinuity in that shear wall. Now, when you have out of plane offset irregularity, this is pretty serious business. Yeah. So elements supporting the discontinuous wall surface have to be designed using load combinations with overstrength factor. That is a very, very important requirement. Overstrength factor for elements supporting discontinuous walls or frames. 12333, that section applies. Then 25% increase in seismic forces, that is almost everywhere for every irregularity. Permitted analytical procedure that you have to look at. 3D model would be required, and even in nonlinear time history analysis, 3D model will be required. The final horizontal irregularity is non-parallel seismic force resisting systems. This building, I do not know what the system is, but if you have a triangular shear wall in a building, that would be non-parallel seismic force resisting system. So the definition is non-parallel system irregularity exists when the vertical lateral force resisting elements are not parallel to the major orthogonal axis of the seismic force resisting system. Okay. It used to say or symmetrical about, and that was deleted in AC 710, which is the main reason I went with AC 710. This is very important. Or symmetrical about didn't make any sense whatsoever. You still have it in BNBC. Do not, I consider it deleted, doesn't make any sense. Non-parallel system irregularity exists when the vertical lateral force resisting elements are not parallel to the orthogonal axis. When you have non-parallel system irregularity, we have to use orthogonal load combinations. And I need to go into that. This is something else that is not covered in BNBC, but I'll cover it right here, not another day. Permitted analytical procedure, whether you have to do dynamic analysis or equivalent static, will do. 3D structural model would be required, whether you do regular analysis or nonlinear time history analysis. Okay, let us look at the orthogonal effects as they're called. The fact of the matter is that an earthquake can hit from any direction. It is not constrained to strike your building along the principal plane axis, obviously. At the same time, if you have design category B, the design seismic forces are permitted to be applied independently in each of two orthogonal directions, and orthogonal interaction effects are permitted to be neglected. So if you have a design category B building and you don't consider these orthogonal effects, you will be fine. Okay. The design seismic forces are permitted to be applied independently in each of the two orthogonal directions, and orthogonal interaction effects are permitted to be neglected. Design category C. What is true of design category B is also true of design category C, and something else is true. So design category B independently in each orthogonal direction was fine. Design category C, that is still fine unless you have a structure that has horizontal irregularity type 5, non-parallel seismic force resisting systems that we are discussing. If you have that, even in seismic design category C, you shall use one of the following procedures. The first procedure is orthogonal combination procedure. Equivalent lateral force, modal response spectrum, or linear response history analysis with loading applied independently in any two orthogonal directions. So you analyze your building independently in any two orthogonal directions under the code prescribed seismic forces, and then you design the structural elements for 100% of the effect of the X earthquake plus 30% of the effect of the Y earthquake, or 30% of the effect of the X earthquake plus 100% of the effect of the Y earthquake, whichever is the worst of the two. So let us say column of the building has to be designed for 100% of the effect of the X earthquake plus 30% of the effect of the Y earthquake, or 30% of the effect of the X earthquake and 100% of the effect of the Y earthquake, whichever is the worst of the two. Okay, let's look at this in a little more detail. So this is a plan view with walls 1, 2, 3, 4 along the edges. Okay, the X direction is to the right, the Y direction is to the top. 4 shear walls. This is earthquake in X direction, causes V sub X in wall 1, V sub X in wall 2, V sub X in wall 3, V sub X in wall 4. Those are shear forces in the walls. The Y earthquake causes V sub Y in V sub Y1 in wall 1, V sub Y2 in wall 2, V sub Y3 in wall 3, V sub Y4 in wall 4. So wall 1 has to be designed for V sub X1 plus 30% of V sub Y1, or 30% of V sub X1 plus 100% of V sub Y1, whichever is the larger of the two. As simple as that. Okay, please look at the pictures and you will see what we are driving at. When it is a column, okay, X earthquake causes axial force P sub X, bending moment M sub X, and bending moment M sub Y. I'm sorry. X earthquake causes P sub X and M sub X. Y earthquake causes P sub Y and M sub Y. The column has to be designed for 100% of the X earthquake plus 30% of the Y earthquake, which would mean for the axial load caused by the X earthquake and 30% of the axial load caused by the Y earthquake, they are additive. But when it comes to the bending moments, it is not additive. You have to design for 100% of the X earthquake and 30% of the Y earthquake at the same time. So now you're looking at biaxial bending of the column. So you have to design for this combination or that combination. 30% of the axial load caused by the X earthquake plus 100% of the axial load caused by the Y earthquake plus 100% of the Y moment and 30% of the X moment. Again, biaxial bending of the column. So this orthogonal effect is kind of serious, but there are important exceptions that I will not go into today. So it's not as bad as it looks. So orthogonal combination procedure, or whatever it was called, that is one way to go. Orthogonal combination procedure. Or the other thing you can do is simultaneous application of orthogonal ground motion. So linear or nonlinear response history analysis, time history analysis with orthogonal pairs of ground motion acceleration histories applied simultaneously. You hit the building with earthquake in the X direction, earthquake in the Y direction, actual acceleration histories, and you do inelastic time history analysis, 3D analysis. Obviously, you have accounted for orthogonal effects very directly. Cannot go wrong with that. Okay. So that is the end of the discussion on horizontal irregularities 1 through 5. We now come to the vertical irregularities, starting with soft story. Okay. So the definition of soft story irregularity is soft story stiffness smaller than 70% of the story stiffness above, or 80% of average story stiffness of 3 stories above. Now, the soft story does not have to be at the bottom, as shown in the picture. Quite often it is, but many times it isn't. Okay. So soft story stiffness is less than 70% of story stiffness above, or 80%, this is or, not and, or 80% of the average story stiffness of 3 stories above. This is a a very nice example of what happens. So this is the city hall of Kobe after the earthquake of I'm having problem with dates today. Yeah, the Kobe earthquake. So in Japan, quite common is what is called steel reinforced concrete. After the war, everything was scarce, and the Japanese built structural steel shapes into concrete, which were discontinued at some point along the height of the building because steel is expensive, and they felt that they did not need all the stiffness up there, where the 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 displacements expected were not large. Or I'm not saying it right. Anyway, as you go up the building, like shear walls are discontinued quite often. You don't need what you need at in the lower portions of the building. Your structure can be less stiff. And so they discontinued the structural steel shapes. From steel reinforced concrete, they went to all reinforced concrete. And in the city hall, that happened. So the steel shapes were discontinued here. And this was the first level. with just reinforced concrete shear walls. So there was stiffness discontinuity at that level. There was higher stiffness below and lower stiffness above. The definition says less than story above, but it can be both ways as long. So that, anyway, you can see that there is a stiffness discontinuity, and the building failed right there, that level. The remainder of the building was not too bad. The building above was not in too bad a shape, but that level pancaked. The interesting thing is the Japanese decided that they would simply remove the building above that level and live with a shorter building. That they felt was the most cost-effective solution to the problem that had been created, which is very interesting, and I have never come across that anywhere else. Yeah. So, and in Kobe, I can tell you that this was almost uncanny. You could you could tell yourself, I want to find a second story, sub story, you will find it. You go around the block, you will find a sub story at the third story level. You go around another block, you will find it at the fifth story level. They were all over, like so many. Anyway, so the sub story irregularity, the only thing that is triggered is this dynamic analysis, permitted analytical procedure. So vertical 1A, 1B are also bad irregularities that would trigger dynamic analysis even for shorter buildings. Extreme substory. Substory stiffness lower than 60% rather than 70% of the story stiffness above, or this is not and, or 70% rather than 80% of average story stiffness of 3 stories above. This irregularity, extreme substory, is prohibited. Design categories E and F, obviously you are not bothered by that. Also, the other thing is the permitted analytical procedure. You have to do dynamic analysis. Nothing else is triggered. Vertical type 2, mass or weight irregularity. This has been deleted from AC 722, not there anymore. but that doesn't change anything for you. Anyway, the definition is story mass larger than 150% of adjacent story mass. Story mass at any story, at one story, whichever story, is larger than 150% of adjacent story mass. In this case, the roof is exempt. A roof that is lighter than the floor below need not be considered under this irregular category. If you have this type 2 vertical irregularity, mass irregularity, then the only thing is permitted analytical procedure. Type 2 vertical is one of the bad irregularities that was mentioned yesterday. Now, this is something I felt compelled to include because this will get you out of many binds. I have found it very useful. And please follow me carefully. It has been pretty long already. I understand it, but please follow me. This is going to be important, I think, for you in your professional life from time to time. Vertical structural irregularities, not just the one we are discussing, but 1A, 1B, or 2, all three. Torsional, extreme torsional, and mass irregularity. Vertical structural irregularities 1A, 1B, or 2 do not apply. They can be considered to not exist, where no story drift ratio under designed lateral seismic force is greater than 130% of the story drift ratio of the next story above. No story drift ratio under designed lateral seismic force is greater than 130% of the story drift ratio of the next story above. Torsional effects need not be considered in the calculation of story drifts. The story drift ratio relationship for the top two stories of the structure are not required to be evaluated. Top two stories need not be considered. Irregularities type 1A, 1B, 2 are not required to be considered for one-story buildings in any seismic design category or for two-story buildings assigned to design category B, C, and D. This is an outright exception. Okay, this thing that I said is important. It gets you out of many binds. So 1A, 1B, and 2 do not apply when no story drift ratio under design lateral seismic force is greater than 130% of the story drift ratio of the next story above. What does it mean? So this is an example of a pretty regular building, 7.9 meters spans in one direction, 6.7 the span in the other direction. This is the elevation. The bottom story is 4.9 meters, the others are 3.7. There are 12 stories, 11 at 3.7 and 1 at 4.9. So the bottom story 4.9 meters, the next story 3.7 meters. So the stiffness ratio is 1 over 4.9 cubed and 1 over 3.7 meters cubed. And that is 0.42. And that being less than 0.6, we have an extreme torsional irregularity type 1B. Okay, so we have vertical irregularity type 1B, which will require dynamic analysis. Okay. Now, the exception that I mentioned, vertical structural 1A, 1B, 2 do not apply when no story drift ratio under. So what it means is that delta sub E1 over H1, delta sub E is elastically computed deflection at floor level 1 divided by height to floor level 1 is less than 130% of the interstory drift of the story above. That would be the elastically computed deflection at floor level 2 minus elastically computed deflection at floor level 1 divided by the story height of the second story. So the first story, at the base, there is no deflection. So the interstory drift of the first story is delta E1. I should have written delta 1E. That was our notation. And anyway, I didn't notice that, obviously. I'd like to write these things down in order to. Anyway, so the interstory drift in the lowest level is delta E1. That divided by the story height has to be less than 130% of the interstory drift of the next level above, which would be delta 2 minus delta 1 divided by the story height, which is H2. Okay. Now we analyze that building that you saw in the east-west direction. That is the left to right direction. And these are the stories, the forces at the various floor levels, the delta sub XC values. These are directly from analysis. This is after we have amplified by C sub D, and this is the uh, the interstory drift. So at level 1, it is the whole thing. At level 2, it is the 114 minus 60, that is 54. This level, it is 168 minus 114, which is also 54. Okay, so you understand this is pretty straightforward. So from the table, delta 1 divided by H1 is 11. No, it's another mistake. No, 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 I'm okay. I just got confused. So we should go with that column.
This
So
is fine. 11 is fine. Yeah.
yeah, yeah, 11, yeah, 11 and 21 are our numbers. Yeah, I just got confused. Okay, so delta sub E1 is 11 divided by H1, 4.9 meters. That is 0.224, and 1.3 times delta 2 minus delta 1 by H2. This is 21 millimeters here, minus 11 divided by 3.7 meters. That gives you 00352. This being larger than that, or this being smaller than that, we do not have to consider type 1b irregularity. This is huge. So we can do equivalent static analysis for this building. We don't have to do modal response spectrum or anything like that. Okay, so please pay attention to this exception and the example. This is PIMA's rendition of mass irregularity type 2. This exists if the effective mass of any story is more than 150% of the effective. I think I can skip it. This is just another representation of what we went over already. PIMA comes up with, pretty good graphics and simple language. This is why I included it. Vertical type 3, vertical geometric irregularity. Horizontal dimension of lateral force resisting system, not the building plan, the lateral force resisting system, that is important. So horizontal dimension of lateral force resisting system in story is larger than 130% of that in adjacent story. So if this is more than 130% of that, then this will be triggered, vertical type 3. This is PIMA's rendition. Okay, same thing. If you have vertical type 3, that is also one of the bad irregularities, and you will have to do dynamic analysis. You have to go to this table, and the table will tell you that you have to do dynamic analysis. Vertical type 4, in plane discontinuity. Okay, this is not an out of plane offset, but in plane. So this was coming down, and then it doesn't, it is discontinued. There is an in plane offset of a vertical. I think the PIMA picture is better. There is an in plane irregularity exists if there is an in plane offset of a vertical seismic force resisting system, resulting in overturning demands on a supporting beam, column, truss, or slab. So if that happens, then there is overturning demand on this beam, the transfer girder. And so this is the definition of vertical irregularity type 4. If you have type 4, then the ASC 7 provisions that are triggered are overstrain factor for elements supporting discontinuous walls or frames. That very important requirement. gets into the picture. Overstrength factor for elements supporting discontinuous walls or frames. Okay. Then 25% increase in seismic forces in connections in diaphragms and collectors. And then the permitted analytical procedure, the type 4. Actually, type 4 is not one of the bad irregularities. So this table, when you go to it, it will require dynamic analysis only for the taller buildings exceeding 160 feet in height. Or the table will tell you that you can do equivalent lateral force procedure. Vertical type 5, weak story irregularity. So when we say soft story, it is stiffness. When we say weak story, it is strength. So weak story lateral strength. This lateral strength is basically the sum of the shear forces that can be resisted by the columns and shear walls in the building. Okay, that's the simplest way to think of lateral strength. How much shear can be resisted by the columns and the shear walls. So weak story lateral strength is less than 80% of the lateral strength of the story above. And it's not and the second line is what I just told you. Lateral strength is total strength of seismic force resisting elements. Yeah. So weak story means lateral strength is less than 80% of lateral strength above story. This is prohibited in design categories E and F, which do not exist in Bangladesh. D to F, you have to go to this table of permitted analytical procedure and figure out if you have to do dynamic analysis. You may or may not have to. Vertical type B, extreme weak story. Now the weak story lateral strength is less than 65% of the lateral strength of the story above. Lateral strength above story. Okay. This is, as I said, the worst of the worst. This is, I showed you this picture, the picture that I didn't comment on. This is from Bhuj. And this is, there is hardly any difference between the other picture and this. This is in India. This one, I don't even remember this. Yeah, I don't remember the place. Anyway, these are all over the world. So this one, extreme weak story, is prohibited even in D. Okay, so please take note that this is something you cannot build. There is a bit of an exception. So vertical type B, structures with vertical irregularity type 5B as defined shall not be over 2 stories or 9.1 meters in structural height. Okay, so it is not that you cannot build it taller than 2 stories or 30 feet. But there is an exception to that. The limit does not apply where the weak story is capable of resisting a total seismic force equal to omega sub 0 times the design force prescribed in section 12.8. So the story is weak compared to the upper stories, but it is very strong compared to the lateral forces that have to be resisted. So in that case, if it is good enough, if it is capable of resisting a total seismic force equal to omega sub 0 times the design force prescribed in section such and such, or if you strengthen your columns to that extent, then you don't have to live with this height limit of 2 stories or 30 feet. This is FEMA's rendition of the 5A and 5B irregularities. And that brings me, so it is not too bad. I concluded when this was supposed to conclude today, more or less. So now I'm open to questions. There is almost a half hour left, which is not bad. Okay, so we'll do it the same way, Bodhi. You tell me.
Yes, Dr. Ghosh. So I will start with the questions from the start. Uh,
Yeah.
okay, so this question is related to the one that I asked yesterday during the break, if you remember, that for soil type SA, the FA value for all zones is 1. For SB, it is 1.2. But for SC, the value is 1.15. So why is it uh, like not gradually increasing, but there's a slight decrease in the values from SB to SC?
Yeah, let me go to yesterday's slide set. Did I shut it off? Yeah. Yeah, I heard that question. This is what the question is on.
No, I will tell you which slide. Yeah, this one.
This one. Okay. Okay. I do not know.
Yeah,
The-
these are the values in BNBC, so it's not mistyped or anything. These are
no,
how the
it's
values
not
are.
mistyped, but I think Dr. Abedin would be the one who knows. He's he has 3 lectures coming up, and I can ask him if you remind me, Bodhi, I'll send the question to him.
Yeah,
He,
Dr. Ghosh, that's what I was telling you yesterday. So
yeah,
the first time when we were preparing this presentation, right,
yeah,
we had the very same question, and you probably asked someone at that time. So
I do not remember.
that's what I was thinking.
Yeah, that's entirely possible, but it's so much going on that I don't remember. This is a good question. There should be an answer. I think he will have the answer.
Yeah, yeah. So that will answer a lot of people.
Okay.
Um, okay, so moving on.
Hmm.
So how do we design a structure near in between resonance range?
What does that mean?
What is a resonance range? Probably is asking if it is if the fundamental period is
I don't understand the question because you don't know the earthquake that will come. So whether the period of your building will be in the resonant range or not, you do not know. Earthquake ground motions are very different. So I do not quite understand the question. And if you want to look at all the historic earthquakes and exclude the entire range where the past earthquakes have been strong, then you won't have much to work with. So I mean, my advice would be don't worry about it. Design your building, properly according to code, and then if there is resonance, that is fine. That the building will still do okay.
Okay, moving on.
Mm.
So vertical irregularities 5B in SDC D, E, and F are prohibited in the states. But if due to architectural reason or the owner needs something that will lead to vertical irregularities, then how they how to abstinence this irregularity?
No, you have to read from the beginning.
Okay, so the question is vertical irregularities 5B,
Mm.
SDC D, E, and F are prohibited in the states. I mean, he means by the code.
Yes.
But if due to architectural reason,
Mm.
the owner needs something that will lead vertical irregularity, then how do we how do we go around that? I don't know.
Okay, so I think I kind of understand the question. Uh, so your question is about type 5B, when I say prohibited in D, E, and F. But I also said that it is really not prohibited. It is, you cannot go beyond 2 stories or 9.1 meters. That doesn't answer your question. The answer to your question is, if your architect must have a taller building that has irregularity type 5, then you have to take advantage of this exception. You have to make the weak story strong enough to resist omega sub 0 times the design force. Okay, it is the way out is provided to you in that exception.
Okay. Then I went over some of the questions myself, and sound problems. I think these are fine. After a point, I stopped. Okay. Yeah, I'll start from here then. For drift computation,
Mhm.
what time period of the building will be used? Is approximate method for computation of time period? Uh, should we use the approximate method or the time period from modal analysis?
Okay, so for drift computation, what period do you use? Uh, it's the answer is it's entirely up to you. So you can do your drift computation under using the approximate period. There is absolutely uh, nothing wrong with it, or uh, how should I say, any restriction on that. You can do your drift computation under rationally computed period t with the limit c sub u t sub a, or for drift computation only, not for force computation. This I did not say, I should have said. You can ignore the limit c sub u t sub a. You can directly use the period that you computed from eigenvalue analysis. The code doesn't care, because I want to explain this. So the stiffness will be, if you use approximate period, the approximate period is shorter than the real period, so you are taking a stiffer building. Okay. If you use a rationally computed period, you are assuming a softer building, a building with less stiffness. If you ignore the limit of c sub u t sub a, you are further decreasing the stiffness of your building. If you decrease stiffness, you'll be calculating larger drifts, and the code has no problem with it. You are shooting yourself in the foot. When it is the other way around, when you uh, try to get out of a problem by making the wrong assumption, then the code kind of tries to restrict it. So the uh, limits of C sub U T sub A does not apply. It would be preferable to use rationally computed period rather than the approximate period, because approximate period assumes more stiffness essentially, but the code never explicitly tells you that you cannot use drift computation based on approximate period.
Okay, Dr. Ghosh. And a subsequent question to this is for drift computation, which load combination do we need to check?
This so I don't know why this keeps coming up. So I kept on saying, I don't know how many times, that gravity loads do not cause lateral drift, any appreciable lateral drift, unless you have a very significant lack of symmetry. Okay, so for the vast majority of buildings, it simply does not matter how much gravity load you have sitting on your structure when you calculate your drift. Okay, but if you want to be code complying, you have I went over that, I think, on the first day of Seismic. I don't remember. There are serviceability load combinations in BNBC. So look at that. It tells you to keep gravity on the structure. I think it is D plus 0.5 L is what I recall. And that is not a bad idea. That much of gravity will be sitting on the dead load will be sitting on your structure anyway. It is a question of whether you want to keep the full design live load or some fraction thereof. And 0.5 L is probably as good an idea as any. So look at that part of BNBC serviceability load combinations, which we do not have in our codes, and go with that. But again, I would say that vast majority of cases it don't make any difference, because gravity does not cause drift, unless there is, again, this is a big unless. If it's a very unsymmetric building, then that is not so. Then gravity will play a role.
Okay, Dr. Ghosh. The next question is, what is the response modification factor for tubular structure?
Tubular structures are not allowed. We will discuss this tomorrow, or when we have strong column weak beam requirement. The columns meeting at a joint have to be the combined flexural strengths of the columns meeting at a joint must be at least 120% of the combined flexural strengths of the beams meeting at the same joint. In a tube, the beams are very deep. Columns are closely spaced. So in a tube structure, you cannot satisfy the strong column weak beam requirement. So a true tubular structure you cannot build in definitely not in seismic design category D. Okay. Now, lower seismic design category, you can do it. What was the question? If you do it, what?
Uh, I went down. No, the question was just the response modification factor for tubular.
The response modification factor will be, that is a good question. I would tend to take something like the, let me think for a second. You as the openings get smaller and smaller, you tend to approach a shear wall core, and that would be an R of 5. So this would be this is one of those undefined systems thing that you will have to exercise your judgment. It will be somewhere between 5 and 8. I will tend to take something like 6.5, no more than that. But this will be only designed up to design category C. I want to emphasize that design category D, you cannot do it.
Okay. So let's move on. Um, okay. Just let me rephrase this question. So the overstrength, do we have to use overstrength factor only for ground floor members or all frames when the building has a soft story?
Let's see.
Yeah, I think what he
Okay.
means
No,
is
no,
that
I know. I
yeah,
understand the question now. So, let us say, a shear wall comes down on a transfer girder, which is supported by columns and so forth. So yeah, follow me closely. This is an important question. So the transfer girder that receives the load of the discontinued element must be designed for the overstrength load combinations. But the entire load path that takes the amplified forces down to the ground also has to be designed using the load combinations using the overstrength factors. So the columns that support the transfer girder, the column to transfer girder connection, the let us say the columns are ground story columns, so the column to foundation, the if it is a concrete column, then it is the column to foundation connection. We do not design the foundation for overstrength factor, but the column itself and the column to foundation connection has to be designed. Okay, if it is a steel column, then it is the steel column, the base plate, the bolts that go into the concrete, but not the concrete foundation. So in other words, the member that is receiving, that the member that is supporting the discontinued structural element, and the entire load path that takes the loading, the amplified loading from the the uh, the transfer girder down to the ground. Okay, but not the foundation itself.
okay, Dr. Gus. If we have columns supporting discontinued masonry wall, do we need these columns to be designed for overstrength factor?
So read it from the beginning. I lost the very beginning of the question.
If we have columns supporting discontinued masonry walls,
Of course, it's not dependent on material. It is discontinued stiff elements. Never said concrete or masonry or wood or steel.
Moving on. This we have already answered. This is already answered. Then, yeah, most of the questions you have answered in your presentation, so I'm skipping that.
Mhm.
There's one question related to seismic zone.
Mm,
So he's saying that Gazipur is
mm,
in seismic zone 3,
mm.
but why is the seismic zone coefficient 0.2 in the table 6.2.15 for Gazipur?
And if that, so he's saying that the table is different from the map.
Yeah, he's saying that the map is showing something Gazipur is in that area. Yeah, this is very specific, probably.
No, it can be specific, but I would be very surprised. Point two is zone two. He's saying Gazipur is shown in zone three.
Yeah, in the map, it is shown in zone 3. Let me also check. I will check. Yeah, part of it is shown, a small part of it is shown in zone 2. If you're looking for the slide number, it is 51, Dr. Ghosh.
51.
Yeah,
Gazipur shown on that.
yes. Let me see.
Uh, no, yeah, I see Gazipur. Yeah, I don't know. From that writing, I do not know on what side of the line it is. So there is no point or anything. So it is showing Gazipur district, I think. The table is talking about Gazipur, the town or the city. And if they have said point two, I would assume that it is uh, in zone two, that the town itself. So I think that's what is happening. I think it is called the district of Gazipur, I think. And this map shows the entire district. The town of Gazipur is probably somewhere here on the other side of the line. So if it is the town of Gazipur, I would go with the table. If it is somewhere else in Gazipur district, then you will have to locate it on the map.
Okay, Dr. Ghosh. If a shear wall is constructed as remedial measure for an existing building up to first floor from ground and doesn't continue above, will it be considered as out of plane offset irregularity?
How is it out of plane? I don't know. Why is
Yeah,
it why is it out of plane?
I will ask him to provide. Maybe he wants to ask something.
Yeah,
Yeah,
I
there's
I
a
I don't quite see what he's thinking. Uh, in plane I can see, out of plane I do not see when I just hear the question.
yeah. This question is not clear. what would be the effect of brick wall in between columns on stiffness?
What would be the effect of brick wall between columns on stiffness? Is that the question?
Right.
Yeah, that is a huge problem. So this is the problem with infield masonry, as we call it. So the brick, not only in Bangladesh, the pretty much everywhere that brick infill is used, the infill is not reinforced. So initially, the infill contributes to stiffness, and the building has very high stiffness because of the infill. But then in an earthquake, the infill is among the first to fail. It cracks diagonally, and then it just it can just fly, even killing people. And when the infill is lost, the the stiffness of the building drops pretty drastically. It goes down significantly. Obviously, not all the infill is lost at one time, but even then, in a significant earthquake, the stiffness will go down significantly, and then the earthquake, the building has a different period. It is in a different range of earthquake. So depending upon the earthquake now may become more critical for the building or may become less critical. You see what I'm saying? Depending upon the predominant period of the earthquake, the lengthening of the period of the building may put it in the critical range or may take it out of the critical range. So what would happen, you do not know. So those who want to play it safe, they design a building that can withstand the design earthquake of the code with the infill intact. And they also design a building that can withstand the design earthquake with the infill all gone. Both ways, the structure uh, should be able to withstand the earthquake. So that the specific answer is the infill initially contributes to stiffness, but the contribution goes away when the infill is damaged in an earthquake.
Okay, Dr. Ghose. Some of the questions are related to model, like response spectrum analysis. These things will be covered by Dr. Ghose in the upcoming webinars.
Yeah.
So I will not address them those right now.
Mhm.
Yeah, because these will be covered, whatever they are asking.
Yes.
Uh, any detailing from collector to shear wall, that we
Certainly.
detailing requirement for collector to shear wall.
Hmm.
So they just want, it's just a general question. Like, are you going to go over that detailing?
I don't know that there is any specific detailing requirement for collectors. I don't know. We have to have the reinforcement that is needed, and then the overstrength factor on the connection. But there is no special detailing requirement that I'm aware of.
Most of our buildings in Dhaka city are soft and weak story. So what can we do now?
That is not a question I can answer. Existing buildings are a huge societal problem. You as an individual cannot do anything. If the owner of the building wants to improve it, wants to spend the money, then you can, then there are several things that can be done. But it is not one solution. Basically, you can increase the stiffness of the building by putting shear walls in wherever there is scope, or you can try to make those columns very ductile after the fact, which is a very expensive solution. And there are other innovative things you can do, but anyway, there are only expensive solutions. So the owner has to be willing to spend the money and engage the right help, and even then it is not going to be easy. the repair itself is expensive and it is disruptive. So the building will probably not be possible to occupy while the repair is going on. So so a building, an existing building with a weak story is a significant problem, and there is no one answer that anyone can give you what you can do. It will depend on the building, what you can do, or what would be a more effective solution.
Okay, Dr. Ghose. There are a lot of questions, so I'm just going over the ones that are relevant. So in your today's presentation, you showed that torsional irregularity is in terms of maximum versus average displacement, but in BNBC, it is in terms of maximum versus average drift. Could you clarify this?
There shouldn't be any difference. So in my, let me see, 1 second.
Yeah, I'm also going. Just checking.
No, this is the wrong one. Now let me look. Now, this is a very good question. I want to make sure before I answer. When when we show deflection in the picture, that may have been loose. Let me see. Story drift. Yeah. So story drift is right. It is not deflection. There is no difference between AC7 and BNBC. We probably should not have used the lowercase delta. We did not mean to. Yeah. Yeah. I think that's a very good point that came out. We should change those to uppercase delta, interstory drift.
Okay.
Yeah, this is very good that it came out. Yeah, as I said, we kind of did it loosely, not thinking.
Yeah, these questions have been answered in the presentation. Any building has been. There are a lot of questions, Dr. Ghose. Yeah, it's hard to go over each and every question, but few of the questions are very fundamental, like
Mm,
fundamental frequency and stuff. Like these stuff is very fundamental things. I mean, even if you are not aware of these topics,
mm.
simple Google search will give you
Yeah.
thorough information. So response spectrum analysis again will be covered afterwards. Irregularities and those have been covered in today's presentation, so I will skip that. So to identify soil type like SD, SC, or SA in BNBC, we have to take the average SPT value up to 30 meters.
Mhm.
However, if the standard deviation is very high, can we use the average SPT value?
This you should ask Dr. Abedin when he comes. I'm not the right person to answer that question. He has 3 lectures, so you should have ample opportunity.
Okay.
The course says average, so most people will just take the average without thinking of how much. But it's a good question. I don't, I don't. I'm not competent to.
Yeah, from the definition of soft story and weak story,
Mm.
uh, we know what they are, but you didn't tell us how to evaluate them. You did. Dr. Ghosh went over it. I don't know what do you mean by evaluate.
I do not know how to tell you the strength. I specifically said it is the shears carried by the lateral force resisting element, and the stiffness is the reciprocal of deflection. So you can judge by comparing the deflections, the interstory drifts again, maybe not deflection, the whether you have substory or not. Interstory drifts are the reciprocal of stiffness.
If shear wall is constructed as a remedial measure out of plane offset, this has been already. I don't know if you were there when we went over this. This question didn't make a lot of sense to us. Can you clarify it more? If shear wall is constructed as remedial measure for an existing building up to first floor from ground and doesn't continue above, will it be considered as out of plane offset irregularity? So this is not clear. How is it out of plane?
We just went over this. Is this
Yeah,
something?
yeah. But this question has been asked again, and that too recently. So I think that he might not have caught it. Uh, I think most of the other questions are very fundamental. So
Okay.
I don't think we'll go over those things.
Okay.
And few of the stuff Dr. Gosa has, you have already replied those things before. So I think better way will be to go over the recordings once more.
Yeah,
Your
no
question will be
matter
answered.
what I do, not every question will be answered. It is it some things require a many years of working and experience and so forth. One cannot answer all the questions you have. It's yeah, it's not easy to follow many times what they. But on the other hand, many good points came up. Some of the questions are really good. So I think these question and answer sessions are valuable. But all I'm saying is, do not expect all your questions to be answered. That's not practical. That's not going to happen.
Right. So before I end this webinar, end the session today, I would just like to inform you guys that I will keep the quiz open. Yesterday's quiz open till tomorrow also because Dr. Ghosh went over part of it
Hmm.
today, our previous lecture. So it is only fair that we keep it till tomorrow. And I will open up the quiz for today in a couple of minutes. And please provide your feedback once again, and we will have another session tomorrow, Dr. Ghosh, and.
Yeah.
Yeah. So thank you for joining in such huge numbers again, and we'll see you tomorrow.
Yeah. Thank you.